Welcome back from the break. I hope everybody enjoyed your short break. We got a really cool conversation lined up where we're going to be talking about behind the cloud at Twitter 1.0. I don't even call it what it's called now. This 2.0 version, I think it's called X or something like that, right? Today we're going to be covering more or less a little bit of introduction about myself. We're going to have some really cool SRE sayings. We got some SREs in the house. Raise your hands if SRE. Yeah. I know DevOps, SRE is one and the same in some scenarios, but we're going to talk about SREing at Twitter specifically. And also we're going to talk about what goes on inside of the data center. I want you all to get ready for bare metal, not just virtualized cloud infrastructure, but we're going to talk about bare metal, talk about Twitter's orchestration platform. Y'all going to see what he paid $44 billion for, so y'all better tune in. We're also going to talk about the history of containers. Big shout out to Solomon. Because I got a really cool story about meeting him at Twitter when he was on his show and tell tour. And then we're going to be talking about solving challenges at scale, really taking some of the learnings that you have developed over the years and understanding that the history that you've been through can influence the next environment that you work in, which is really the real asset, which is knowledge. So, the blue bird. Who remembers this bird here? Some of y'all? Yeah? Big shout outs to the bird. It's not blue what it's normally, but definitely is by far one of the best jobs I've ever had. And yeah, big shout outs to X now, even though, yeah, whatever. My name is Bobby Dorlus, but my friends actually call me Bobby D. So when y'all see me, make sure y'all say what's up. I've been in the field of engineering and technology for 20 plus years. I've been at the keyboard. I've seen some Red Hat staff here. Big shout outs to Red Hat. I see them over there. I've been RHCE Red Hat certified as an engineer since '06. I'm actually coming up on 20 years since being certified. And technology and engineering has always been my life. As up there it says, I've been there, worked at Twitter for almost 10 years. And my role at Twitter was a staff site reliability engineer. And I was the team lead for the compute platform. It's a very unique skill set to work at that level. But just think of, in terms of the role itself, we're managing infrastructure at scale. The main key points we're going to be hitting today is we'll definitely have some SRE mantras. So look throughout my slide. You'll see some SRE mindsets and concepts that we'll be talking about. Talk about working and running one of the world's largest compute clusters. We'll also talk about, at the end, about CapEx, capital expenses. CapEx is basically the costs that you have to pay next year to continue to run your services, right? If you're running anything in AWS and GCP, that's how they lock you in, right? Next year, you're going to be paying just as much, but hopefully even more, right? And we'll talk about the technology, Cgroups, Namespace, Solaris. Anybody ran Solaris? You know Solaris? Yeah, just a few. I'm one of those old head engineers that's been around for a while, so you'll definitely hear me talk about some technologies that's no longer here, but you'll see why I bring it up, because it has influenced the infrastructure, systems, and computing that we're using today. And then we'll close it out with a really cool story. Y'all like stories? I'm a great storyteller, so I'll definitely show you all about a journey that I went on supporting other teams called the compute versus storage, but definitely having a massive impact in terms of the opportunity. Now, this is what most people see when they think about behind the cloud, right? I've worked in environments like this, maybe not as bad as this, but I don't know if about y'all, but I don't think I'm going to pull any cable out of that room there. Might bring the whole site down. But what we're going to be talking about specifically is Twitter's infrastructure. I didn't put a barcode here because I want y'all to go and follow me on X. My name is up there. It's BobbyD_FL. This slide, or actually this article, is pinned to the top of my Twitter account. Yeah, I can still call it Twitter. But in general, this article really gives the world an insights into the type of infrastructure we built at Twitter. A lot of misconceptions about what the actual platform and infrastructure look like. And one of the cool things that I'm here to show y'all today, this is what he spent $44 billion in terms of the computing infrastructure. This right here is actually the whole platform in terms of what we've built internally. I know some of the names are looking a little confusing. They're like, what is this and what is that? We always like to name things ourselves. Obviously, we like to use bird names. But more specifically, if we compare it to what industry-wise, in terms of open source projects that are out there, you'll notice that this technology is really driven off of utilizing open source services or building stuff internally, and definitely the industry has taken advantage of some of the stuff we built. I'm not saying we made contributions to all of these, but in terms of just understanding what the infrastructure looked like, I'm hoping that these normal terms in terms of platforms and services gives you an insights into what we built at Twitter. Now, we're going to be diving not just up at the top layer, but we're going to be jumping into the platform and then down into the data center. But one of the cool things about working at Twitter, which I didn't know when I got there, is that Twitter actually built their own data centers, or we built our own data centers. Not just own data centers, we actually built our own computing infrastructure and hardware. So it was really cool to be in an organization where we can go from platform all the way down to actual floor or groundbreaking infrastructure. I was actually part of the team that actually builds infrastructure. So when they decided to pick a site, I was one of the first ones with the golden shovel, you know that golden shovel, and they're cutting the line, right? That's where my first starting at Twitter started at, is building the infrastructure from the ground up. And this image here is an illustration of what bare metal data centers look like. Just think of it, a warehouse, and we stack computers from the floor to the ceiling. But once you get inside, you'll start to realize that we design things to be extremely simple. Simplicity is key. And this article that gives us more details about what we build internally, you'll see here that there's a split, almost 50 to 50%. The 50.6%, that was basically all the computing resources that my team supported. And what I mean by that is, when we looked at one of those data centers in the building, my team of about no more than 8 engineers supported about 50% of all those nodes, physical computers, bare metal, right? And what does that look like? This is actually an illustration of a row of nodes inside of a data center. And just think of this like thousands of rows, just line after line. Quick story, I remember the first time I visited a data center, I didn't really comprehend how massive the infrastructure was until I was standing at the beginning of the aisle. This is aisle number 1, and way over there is aisle number 100 something. And I'm looking down the aisle, and all of a sudden I see, like, you know when it gets real hot and then you see like a mirage, like a wave of heat? I was like, oh my gosh, we're running compute. We're running massive infrastructure that I can see the heat rising down the aisle of infrastructure. But the cool thing about what we've done in all of these computing resources is we were able to manage this type of infrastructure with a very small team. At the bottom of this slide here, you'll see 10 to the power of 1 of engineers. We had no more than 10 engineers on our team managing all the way up to the top 10 to the power of 6 CPUs. That's millions of CPUs in one of our data centers. And whenever I talk about this, especially managing bare metal, remember, we're not virtualized and running on a hypervisor. We're actually running at the bare metal level. People ask all the time, like, how were you able to manage this? Here goes one of these SRE mantras, right? As an SRE, one thing that I've always taught my mentees is that you should be automating yourself out of a job. I know it sounds weird, and every time I explain it, most people are like, I don't want to lose my job. Actually, what happens is once you automate a task or something called toil, you heard of toil, right? I seen it up on the slide, right? As soon as you automate that toil, guess what that does? It opens up for more opportunities for you to work on bigger problems and solving bigger challenges. So as my team, being a team lead, really needed to understand these type of mantras and honor it, because literally my team had automated ourselves out of roles of managing the bare metal machines. Now, when we actually take the step further, we talked about the physical building, infrastructure, bare metal machines. You still need some type of computing platform in the environment for us to schedule workloads. And we're going to be talking about the compute platform, which is my team. Well, it used to be my team. I'm still wholeheartedly still at Twitter in my mind. But big shout outs to compute. One of the things I mentioned in early slides is that we ran one of the world's largest compute clusters. It's not something that we told out loud because obviously they wanted to keep things quiet, but we ran hundreds of thousands of nodes around the world. Hundreds of thousands of bare metal machines with 10 engineers. Now, when you think about the big statement here, what does behind the cloud looks like? One of the technologies that had allowed us to grow massively and really understand where we can go in terms of capacity endlessly was leveraging something called containerization. And we're going to talk about the actual compute platform even more. But one of the cool things about coming to this conference is I got the chance to meet Solomon. Have y'all got a chance to meet Solomon? Give him a big round of applause for his conversation, right? Because one of the cool things about Solomon, in terms of the team that he built or the concept around Docker, is that it actually had some systems and services that preceded it that if you manage systems prior and you see where Docker was going, you were happy that the Linux kernel was starting to adopt the concepts of containerization and providing those isolation. Because I'm going to give you a little history lesson here. Some of y'all may not have been around in 2000 in the field. A quick show of hands. How many's 1 to 5 years in the industry? 1 to 5 years. Raise your hand. 1 to 5. All right, 5 to 10. 5 to 10 years. And 10 and more. 10 and more years. All right. So y'all know what I'm talking about here. All right. So 10 and more years. You know that there was a few different operating systems that really influence where we are right now. One of those that is key, and I shouted it out earlier, and I think, I don't know, Red Hat is here, so I'm going to say it's the second to best operating system created was Solaris, a Unix operating system. And real quick about Solaris, the reason why it was so good is that inside the kernel, it actually had a very limited amount of system calls. Basically, it didn't have to do what the Linux kernel had to do, which is be able to support every hardware that ever was invented, versus Solaris was very narrow focused because they've created some really cool hardware. But back to our conversation about containers and the history. So I kind of jumped in the game probably around 2001, 2002. 2004, Solaris had this concept around zones, Solaris Zones. It's basically providing an isolated space for an application to run in, and you define what its limits are. If it exceeds those limits, such as CPU, it would throttle it back. If it exceeds memory limits, it would just kill the process. This sounds familiar in terms of what we eventually had in our environment, which is containerization. But big shout outs to the big G, Google, '06. They came out with Cgroups, and it was actually able to get merged into the kernel. And then Red Hat, you see I always shout out Red Hat. Red Hat in '06 introduced namespace. But the thing that really took us over, and I can't shout out the big blue, IBM, right? Is containerization from Docker's perspective changed the game for everyone. Because what happened is that before, if you didn't hear what Solomon said, we actually had to build your own kernel to actually enable certain features such as namespace and Cgroups. Versus, now that it's built in the kernel, you still had to have a really elegant interface, right? We wanted to make it easy. You see Docker image, and it pops up an image, but then Docker deploy. Like, how is this going to not blow up? Quick story. So back in 2013, 2014, Solomon was doing his show and tell tour, and he visited the Twitter office. We used to have these lunch conversations where people in the industry, I lived in San Francisco for a good time, and one side note, what y'all have here in Tel Aviv, big shout outs to you. Because I went to a meetup last night, and it felt like I was in San Francisco, and that same vibe, that same feeling, because I seen what you all were building. So one thing, big shout outs to the organizers, big shout outs to what you're doing, because the thing that was cool about working in Silicon Valley is when you get out there, I'm like Team Twitter, like Bluebird every day. And then you go to a meetup, and then you meet Google engineers, Facebook engineers, this engineer from that engineer. And I'm like, why are y'all over there talking with each other? Aren't y'all in competition? Actually, it's not like that. Actually, everybody's working together, working on projects. And that's why when Solomon said he went to go do a show and tell, he was visiting everyone's office. And one of the cool things in 2013 is that we got exposure to a really cool interface that allowed you to schedule workload, but also take advantage of file system isolation, which was key, but then leveraging things inside the kernel. So big shout outs to Docker, big shout outs to everything that they're working on. And yeah, we're going to dive deeper into what the platform looked like. Remember where the history in terms of containerization, Twitter didn't use Docker, but we'll talk a little bit why. But when I saw it, I already knew that we would be here this time 10 years later, right? So this is what the compute platform looked like. This illustration is very simple. It's simple on purpose because that's what the infrastructure itself looked like. We had a scheduler that basically managed when tasks were being scheduled, and then we had an orchestration system called Mesos. Anybody familiar with Mesos? Heard of Mesos? Yeah, I heard people 10-year plus, so y'all definitely run into it. If you're not familiar with Mesos, just think of the platform predecessor before Kubernetes, right? So Google released a Borg paper, or paper on Borg, which is their scheduler that they're using. And then guess what? The open source community went and go develop our own. And one of those that came out was Mesos. Twitter was smart enough to go, poach the PhD students that were writing these papers around Mesos, brought them into the office, and we actually developed Mesos internally. But the cool thing about this design here is that you can see that the scale itself allowed us to grow massively. Because down at the lowest level, you'll see there's JVM.30 or 89, there's WebApp.24. Those are instances of applications running in our massive infrastructure. And one of the cool things about Mesos is that it looked at that data center that we talked about as one computer or one operating system. And actually, I kind of think of it as at the kernel level, right? And then the scheduler is right above it. But once we were able to introduce infrastructure like this, we were able to be massive in terms of the amount of workloads and containers that we ran. One little side note, our cluster, at least one of them, would run well over 500,000 containers in one cluster. 500,000 containers, and I was the one that was responsible for it. You know how many sleepless nights I've had? How many of y'all know what PagerDuty sounds like? One of the worst sounds in the world. But anyways, let's talk a little bit about Mesos, the infrastructure, and then definitely kind of bring it all together, what we've built at Twitter. So Mesos, as I mentioned, was more or less looking at the data center as one unit, right? And our main thing were computing resources such as CPU, memory, and disk, right? Also networking, but primarily CPU and memory. The cool thing about the Mesos infrastructure is it leaned on a lot of other open source projects out there. Anybody's familiar, remember about Zookeeper? Yeah? Probably before etcd type stuff, right? But the design and more or less the cool thing about Mesos is that it was an orchestration platform that looked at the data center as one OS or one computer, and then you could actually add other kind of schedulers. At Twitter, we only ran one scheduler, and that scheduler was called, I apologize, next slide, Aurora. But before then, what I wanted to do is to make the correlation between Docker and what Mesos Containerizer was. If you see the diagram there, it is very similar in terms of design. That's why when Solomon pulled up to the office, there were some of us sitting in the back like, I wonder who was talking to him about designing it like that. Because definitely it really was influenced by some of the things that we were doing at the office, but also past history. That's why the similarities come up. It's very simple in terms of the concept, right? Bare metals all the way at the bottom, and as you're working your way up, you're adding slight layers, providing API access. Everything should be an API. I don't know if anybody's ever told you that, but everything should be an API, right? And then obviously the agent in terms of process itself. But the main corporate that allowed us to schedule all of our workloads and to be able to have 500,000 containers out there was Aurora. Now, the cool thing about Aurora itself is its design was really influenced by the Borg paper. If you haven't had a chance to check it out, I would definitely go to Google's site, engineering blog, look for Borg, B-O-R-G, and definitely take a good read of it. You'll start to see the similarities of what you're using right now in Kubernetes, but also big shout outs to Nomad, because the concept itself, HashiCorp, definitely gives you an idea of what their infrastructure is also built off of. But the really cool thing about Aurora, there was this concept, or not concept, but there was this kind of little shade that I seen was thrown about this data structure file system thingy called YAML. How many of y'all know about YAML? Y'all like YAMLs? This is why we didn't do YAMLs. Because we thought that when you're actually defining what your application should be in terms of its state, we decided to do something in terms of a DSL, create it to look very similar to a programming language called Python. We really liked the concept because it was writing code to define your state rather than defining a JSON or a YAML. Unfortunately, everybody didn't get the memo because now we see the issues we have with the YAML. But the cool thing about Aurora is that you can define your application just like code, in terms of just like a Python and code. And this is very simple. It's a JVM app that you can kind of walk down and read it, which is why I love Python. It's a very phonic language. The way it's written is the way you read it, and then obviously there's so many libraries. But one of the cool things you can see down here is that you can kind of define not just the application, what's going to be the runtime, how to start the application, but also how many instances of the application. So we're going to actually schedule some workload right now and just jump right into it. So we're going to take those 6 nodes there, and we're actually going to be scheduling workloads on those nodes. So just imagine each of the little blue boxes a space where a container can be scheduled. So remember in our configuration, we said we want to have 20 instances of the application running. So what does that look like? Each of those yellow boxes right there is 20 instances of the app. But as an SRE, just imagine if I'm scheduling workload in a data center and I'm scheduling it within 2 racks, what kind of problems are we about to deal with? Potential reliability. If 1 rack goes down, you can have more than half of your service go down, right? So the design strategy is always that you want to keep those same concepts in play when you're designing a system to be able to schedule those workloads. So inside that Aurora configuration file, remember we're defining it in Pythonic code, I can say, hey, there's different limitations so that if 1 rack goes down, it doesn't bring down my whole service. If 1 host goes down, it doesn't bring down my whole service, and you just define it inside your Aurora config. But the cool thing about Aurora itself is that if you do define this state, and then all of a sudden 1 of the racks go down, like a rack, bare metal, that blue row, 1 of them goes down, this is where the beauty of an orchestration system, because we're always checking to see if your services are running, and we will easily just schedule the ones that went down on another set of racks. This is the hidden mirror. This is how we were able to do some massive infrastructure changes in our environment without impacting the whole world. And what I mean by impact the whole world, I mean 1 command can bring it all down, right? And that's why we design systems as such to keep this in mind in terms of reliability. Now, one of the coolest things that I've ever experienced is rolling a production cluster. Now, what I mean by rolling a production cluster, remember we're talking about a data center, thousands of nodes, thousands of roles, right? And when I say rolling, we're going to do 1 or 2 things: update the operating system, patch it, and do some type of maintenance. Imagine if you have hundreds of thousands of nodes that the world depends on, and I can reboot every single one of those computers within 20 to 30 hours. It's amazing. Soon as I had access to this and I seen what it was capable of, the game changed for me, right? Because remember, automation. Oh, I can automate this thing? A task that would take us almost a month to complete, we were able to complete it within 20 to 30 hours. Yeah, I was sold. And one of the cool things in terms of a mantra that I want to make sure I emphasize here is keep it simple. Keep it simple. Simplicity is the key. Also, go deep in understanding, right? A lot of the things that I always encourage my mentees is to understand how it all works, not just that abstracted layer. If y'all didn't know, that is the hustle, is abstract it all away from you, and then you guess what? We can charge you anything we want. That's what AWS, GCP, and Azure are doing, right? They abstracted away so much that now those bills, in terms of that CapEx, yeah, I know you've all seen it. And then always know that once you're able to really go deep, keeping it simple, the scaling parameter is limitless, right? You can go beyond the limits of what you're scaling because the infrastructure is very simple. Now we're going to jump into a quick story here. Talking about compute, talking about storage, which are 2 separate teams. And the thing that we really ran into is that if you think about the infrastructure, we have half of the data centers for compute, and then the other half of the data center is storage. What does that look like? We ran storage infrastructures from Hadoop. I know Hadoop, anybody's run Hadoop? Yeah, HDFS, yep. We ran one of the world's largest Hadoop clusters, petabytes. Manhattan was a key value stores like Cassandra, and also blob stores like our image store, right? So any image that was ever, or any image that you view is stored in a blob store system. It's like an S3, right? And in terms of their infrastructure, it was simple also, right? You had somebody that was managing where all the bytes and bits and pieces of data were stored. You talk to that coordinator before you go and fetch the data, and then it sends it back. Whoever sends it faster basically gets, a +1 type thing. But this infrastructure itself had some challenges because we actually went through this process at Twitter, which is a note here about toil, is differences in your environment creates more toil. Imagine if you're managing hundreds of thousands of computers, and now you got to make a computer for your storage system, but Blobstore wants this computer, Manhattan wants this computer, Hadoop wants this computer. Those differences creates more toil. So keeping it simple in our infrastructure was like everybody gets the same type of computer. But there was a side effect. One of the side effects were, man, everybody got the same computer, but inside this data center, we're not utilizing all the resources to their full potential. This diagram right here shows CPUs only 6%. These are storage machines. Yes, there's going to be a peak in disk performance, but you also notice that the network interfaces are only using 20% of the network interface. And they actually have two 10-gig network interfaces. We're not even using the second one. There's a project that we actually went on, and this is probably one of the last projects I worked on, looking for inefficiencies in the data center. And when we went to go do this investigation and we pulled up this chart, it actually wasn't one computer. It wasn't two. It wasn't 10. It was tens of thousands of computer running and only 8% of them being used. Now, this is where I want to encourage you as SREs and DevOps engineers in your organization, is that this is where you are able to step in a role to support the bigger picture, not just your team, but the bigger picture. Because this was a chance for me as a staff engineer to move into a senior staff role and reaching across the aisle to touch another organization. One of the other bigger ones on there being storage. And I basically had this conversation. I brought up the same slide with the storage team. And then all of a sudden I was like, how can I illustrate to them what we actually have as a challenge? So I was looking on the internet and I was like, yo, can I just show them? If they have a car and you put this massive engine right on top of it, this is what they were running, right? And what we found out is that this inefficiency actually had a dollar value with it. And what we discovered is that if we use this technology called, containerization, we could really help them out and really like change the game in terms of what those nodes are doing inside of our data center. So what we did, and this is what inside of a computer looks like, right? CPU memory disk, is that we understood exactly how the storage systems work. Remember, diving deep as an SRE. I wasn't on their team, but I went and dived deep. And I was like, yo, if we're using 8%, why don't we just take whatever they're using and put it on one CPU, and then we have a whole nother CPU available. And you know what? There's something that came available in Red Hat, CentOS, called Systemd. Y'all know what Systemd is, right? How many know what System 5 is? System 5? In it? Yeah, there's only a few. Before Systemd, System 5, but Systemd had the ability to split the hardware right down the middle by using something called Cgroups and Namespaces, right? But at the operating system level. So once we understood this, we were like, you know what? What if we just put the storage system over there, and now we have this whole other side of the bare metal machine that we could easily just put compute workloads over there. Eureka, there we go, right? Now this design strategy went from this to this. Now we're utilizing the CPU 60%. And now you see there's two network interfaces. Yes, there's still spiking disks because Mesos, the compute side, didn't really care about disk, right? And we actually were able to really make an impact to computing resources out in our fleet. And remember, this isn't 1, 2, 10. This is tens of thousands of computers. So that I like to show this chart here because the impact that I had was about 9% of the data center. When I originally was pitching this slide to Twitter, when I was traveling and talking about this, they said, yo, I can't tell the world how much. Now that it's been sold, I don't really care no more. So this slice of pie right here is actually, we projected that we were going to save about $130 million year over year. We actually missed it a little bit. We actually saved about $122 million year over year by making that infrastructure change. And this is key because the thing that I always mention as a mantra to my team is like, if only we win, the compute team win, then we failed, right? This is a prime example where the things that you all are developing, right? Sometimes you feel like I'm making my team great, but guess what? The organization itself is still lacking, right? Is if we win, we've failed. What I said is like, yo, we have to go over there and support. We have to make sure we show other teams like we have automation, we can really make a change to it. I think that alarm is for me. We're almost done. But big shout outs to the whole squad. I couldn't do this, have done it by myself. It definitely is a team effort. And definitely want to give all these people big shout outs. Some of them are working at some big companies now, Google, Facebook, Roblox, and all of much, right? But definitely it's not something that can be done by yourself. And I only got, 2 more slides just to shout out. I do run an organization called the Tech Hustle. It is a company organization that's looking to motivate, inspire the next generation of engineers. We have a very vibrant newsletter, so if you are looking for some good comedic conversations about tech, definitely from a different perspective, because you may not have heard it from somebody like me, definitely check us out. And yeah, Tel Aviv, I want to say thank y'all so much for allowing me to pull up and present. And definitely, if you see me later, make sure you holler at me. Thank you so much.